Okay, welcome to lesson 7.7. We're going to look at some applications of dot and cross product today. So the first application we're going to look at is called work. And so we're going to figure out how much work is done when a force is acting on an object so that the object is moved. So when we move the object, we call the distance that it moves the displacement. So the vector S is going to represent the displacement of the object. And that displacement is going to be in meters. So that's something that you need to check for. If they give you the displacement in centimeters or something like that, you have to convert it to meters before you get started. And the vector F is going to be the force that's acting on the object. And that force is going to be given to you in newtons. Now, because this is like a new unit, they're going to give it to you in newtons. They're not going to make you convert. So that one should always be given to you. And W then will represent the work that's done. Notice that W is not a vector, and I can see that because W is equal to the dot product of the force and the displacement. So I know that the answer to a dot product is just a scalar, and so that's why W is not a vector. And so W is the work done, and the unit that we use for work is joules. So those of you who've taken physics are probably more familiar with these units of newtons and joules. Our first example here, we've got a box is being pulled a horizontal distance of 100 meters by a force of 500 newtons applied at an angle of 30 degrees to the horizontal. And we're going to calculate the amount of work done. So I'll draw a bit of a picture here for you. We've got the displacement of the box. The box is being displaced a distance of 100 meters. So something like this, and then the force that's acting on that, it is applied at an angle of 30 degrees. So I'm going to try to draw this, with an angle of about 30 degrees, so just less than the 45 diagonal, something like this. And that one's quite a bit longer, right? Like 5 times longer. So there's my force vector here. And here's my displacement vector here. And the angle that we're talking about when we talk about work is the angle between the tails of these two vectors. So there's my theta there. So when I calculate, I'm calculating the amount of work done. So I'm going to use the formula work is the dot product of the force and the displacement. And you'll find this formula here in the box that's on your formula sheet for this test. And so because here I'm given the magnitude of the force is 500 and the magnitude of the displacement is 100, I'm going to use the version of the dot product formula, which is also on my formula sheet, where it's the magnitude of the two vectors being multiplied times the cosine of the angle in between them. And I have all of this information. So the force has a magnitude of 500, displacement 100, and then cosine of 30 degrees between them. And so I'm just typing that straight into my calculator, making sure I'm in degree mode, and I get 43,301.3 joules, and that'll be rounded. And sometimes what you'll see in the answers is they convert, especially when it's such a big number of joules, is they'll convert it to kilojoules. So if I think about like meters and kilometers, there's a different, like there's a multiplier of 1,000 between the two. So when I'm going to the bigger unit, I'll divide out. I'll just put that in a different color. I'll divide out by 1,000. And so that would equal 43.3 kilojoules. And then we'll write a sentence here. So on your test, whenever I have a word problem, I do try to give you a bit of a hint about the unit, because you're going to see with some of the other ones the units are different. And again, I'll tell you how many decimal places to round to. All right, our next applications are areas and geometric figures. So we're going to look at the area of a parallelogram, and two of the sides of the parallelogram are formed by the vector A and the vector B. So they're going to be the two of the sides that touch each other, and you can kind of see that the other sides would also be vector A and vector B if I were to slide them over. If I want to find the area of that parallelogram, I just do the magnitude of the cross product. Where A and B are the sides, and theta, again, is the angle in between them. Similarly then, the area of a triangle, you can imagine here I would just be cutting the parallelogram in half. So the area of the triangle is just half of the area of the parallelogram, so half of the magnitude of the cross product. And here, when you look at a triangle, sorry, let's just move this so the watermark's gone. When we look at a triangle, when we talk about vector A and vector B being two of the sides, I want you to imagine that vector A and vector B could be two different sides. Like somebody else could have called this vector A and this vector B, and it would be the same formula because the parallelogram now is just off to the other side of the vectors. So it's the same formula. It doesn't matter which two sides of the parallelogram that you have as long as your vectors are tail to tail and the angle is in between them. Okay, so we're going to determine the area of a parallelogram formed by vector A and vector B. So we're given those vectors in component form. So we'll be using that version of the cross product magnitude. There is another cross product magnitude formula that involves the magnitudes of the vectors and the angle in between, but we don't have the angle in between, so we'll just go with the cross product formula. So I'm finding the area of a parallelogram. So it's just the magnitude. Not a half, right? The half is only for a triangle. And in order to come up with the magnitude of the cross product, I'm going to find the cross product of these two. So I'm going to, use that here I've already deleted the top row and the bottom row of my memory trick, and I'm just going to go through and do A2 times B3, so I get -6, and then A3 times B2, and I get -1, but I'm subtracting that, and then we'll keep going A3 times B1, so that's -1 times 0, and then I'm subtracting A1 times B3, and I get -3. And then we'll do A1 times B2, and I get 1 minus, and then A2 times B1, that's also 0. And then we'll simplify out. We've got now that vector resultant of A cross with B, and I get -5, 3, and 1. And now our final step will be to find the magnitude of that vector, so the square root of each of those components squared. So you could have set this question up slightly differently by finding the cross product alone first and then saying that the area is equal to the magnitude of that vector. Like if you wanted to do this step of finding the cross product off to the side and then bring the answer in, that's fine as well. And when I add that all up underneath the root, I get 35. I can't simplify that, so I'm just going to leave that and say therefore the area . And since I'm talking about area, the units are squared. We don't have the units here. We're just in a coordinate grid, so we don't know the value of a unit, so we just say units. All right, our last application that we're going to look at this year is torque. So torque is a rotational or turning effect about a point A created by a force F acting on an object located at point B. So it's kind of a lot of terms there and points. So I've got my point A here, and what I'm gonna do is apply a force, and so I always imagine the force actually coming in from this side here, and I'm pushing on that point B, and what's going to happen is it's going to turn about this point A, so it's going to rotate. So a lot of the examples that you'll see, and you can see it in our example below, is like a wrench turning like a screw. So I've got here, I'm going to turn this guy around. Another example that you'll see is like this is the axle of a bike, and I'm talking about the pedal here. I'm applying a force to a pedal, so you'll see that one as well. When we talk about torque, we use the Greek letter tau. And so that's this like funny T symbol here. So it is a vector where we're talking about torque, which has a direction as well as it has a magnitude. So the torque is equal to the the length, the distance between the point where I'm turning and the point where I'm applying the force, and the force vector itself. I can find the magnitude of torque just using that formula that we have for the magnitude of the cross product. So taking the magnitude of each of those vectors times the sine of the angle between the tails. So notice here that they've put the angle on the outside of the triangle formed here by the head to the tail. So if they gave you this interior angle here, we're actually talking about this one out here. Now the thing is though, we're actually talking about sine of the angle, so it won't affect your answer. So if you used like an alpha angle in here or the theta, because it's the sine, think about the cast rule. If I'm in the A quadrant or the S quadrant, I'm going to get the exact same answer if I'm talking about the same related acute angle. So I'm going to look for you subbing in the right angle, but it won't actually change your answer. All right, a note again, R, that distance between where the force is being applied and where the rotation is happening must be in meters again for the units to be in joules for my answer. So my torque units are usually in joules. All right, so in our first example, we've got a wrench. It's 30 centimeters long, so this distance here is 30 centimeters. It's being used to loosen a bolt by applying a force. So the force has a magnitude of 20 newtons, and then the force is being applied. It makes an angle of 150 degrees with the wrench. And so they're giving me that outer angle that I'm looking for. We're going to find the magnitude of the torque. So they only want the magnitude. Watch out for that. And when they give you the magnitudes and the angle, the only formula that I have that's useful here is to find the magnitude of the torque. I can't find the direction. So in this one here, I'm going to be using this formula. But what I notice is that they gave me the length of the wrench in centimeters, which is not okay. I need to figure out the length of the wrench in meters. So to convert that to meters, I'm going to divide by 100. There's 100 centimeters in a meter. And so I've got 0.3 times the magnitude of the force is 20 newtons times sine of 150 degrees. All right, so we'll type that all into our calculator and it comes out to exactly 3, and the units are joules for torque as well. So therefore, lots of therefore sentences, right? When we're talking about word problems, you should have a therefore sentence at the end. Okay, 3 joules. And that's it for this lesson. Enjoy your homework, and don't forget to get started on that summary sheet before you do the review questions.